Hello all, welcome to the next lecture on microwave engineering. So we are discussing the unit 1. In the previous lecture, we have covered the analysis, the analysis of TE wave propagation inside a planar waveguide. So wherein we have calculated the field components that are present inside the waveguide. Okay, so the final equations that we derived for the TE wave propagation are like this. So we found that Ex and Ez will be 0. So the only component of electric field that exists for the TE wave is this. So Ey is equal to C1 into j omega mu by h square into m pi by d or m pi by a, whatever it is, a or d, which represents the difference between the two plates or distance between the two plates, which is the dimension of the waveguide, sine n pi by d into e power minus gamma z. Similarly, the h components hy will be 0. Okay, so we have two h components, hz and hx. So hz is given by c1 into cos of m pi a or m pi d into x into e power gamma z. And similarly, hx is equal to r into m pi by d h square into c1 sine of m pi by d into x into e power minus gamma z. So, how these equations are derived, that we discussed in the previous lecture. So, you can go through that previous lecture if you have not seen it. Okay. So, these are the field equations. Okay, the field equations for a T wave, for a planar wave, right? So, we derived these expressions by doing the analysis, right? Now, let us continue to the next topic. So, the next topic in our lecture series is the characteristics of TE waves. Okay, so whatever the TE waves that we derived, okay, the field patterns are derived here. From these field patterns, we define certain parameters or characteristic terms that are related to the TE waves. Okay, so what are these? Right, let us discuss one by one. So as I have listed out the parameters that are related to the TE waves. So firstly, we will discuss the field patterns, the visualization of the field patterns. So we have derived the equations. So how does these equations look like? Okay. So what is their variation? Right. The visualization of these field equations is what we call as field patterns. So we will discuss that. We will discuss that first, and then what is mean by mode order. Okay. What is mean by mode order, and what do we mean by mode? Okay, so that we will describe, and for this what is the minimum mode possible for the TE wave, that we will discuss. After that, we will calculate the cutoff frequency, right? So what is this cutoff frequency? Why does it come into picture, right? And what is the expression in case of TE waves? We will calculate. And then similar to cutoff frequency, we have cutoff wavelength, that is the maximum wavelength that is supported by the waveguide. And third is the launching angle. So launching angle is the angle with which what is the angle with which we have to launch the EM wave into the waveguide, so that it propagates in the required manner. Okay, that means we will get the field pattern as per our requirement, that is the number of modes, etc, etc, all these things. Okay, so we will discuss one by one. Okay, so let us start our today's lecture. So first thing, so field pattern. So so that is a visualization of the fields inside the waveguide. Okay. So if you look at this, right? So the three equations that I got for the fields are Ey, Hz, and Hx. So firstly, if I look at Ey term, so if this is my waveguide, okay, planar waveguide. So this is my conductor, and this is another conductor. So this is placed at x is equal to 0, and this is placed at x is equal to d or a. Okay. So we can see that the Ey is a function of d, right? Is a function of d. Okay. So sinusoidal variation of d or x. Okay, isn't it? So all these three functions, all these three terms are basically variations of x. Okay. So the field patterns are nothing but the visualizations that are obtained by varying the x value from 0 to d. So if I apply, for example, if I put x is equal to 0, so what I get is sine 0. Sine 0 means 0, right? Okay, so this entire term goes to 0. So Ey, for example, if let us take Ey first. Okay, so when I put x is equal to 0, what I get is sine 0. So remaining whatever it is, this entire Ey term becomes 0. Okay, so right, at x is equal to 0, my Ey is also equal to 0. Next, as I increase the x value, as I vary the x value, right? Okay, so we can see that we will get a sinusoidal variation, right? Now, when I put x is equal to d, right? When I put x is equal to d, so that means this is d. So d gets cancelled. Sine of m pi. Okay, sine of m pi is again equal to 0. Okay, so when x is equal to d, I also have, right, my Ey is equal to 0. So in between this, in between x equal to 0 and x equal to d, it varies sinusoidally, right? It varies sinusoidally. So therefore we can have, right, a sinusoidal variation like this. Okay, there can be one half cycle. Okay, there can be one half cycle. There can be two half cycles, or there can be three half cycles, right? We can get a variation like this, or we can get a variation like this, or we can get a variation like this also. Okay, so this is one. This is. So right, when m, right, when I have m equal to 1, so this basically the number of half cycles basically is dependent on the value of m. Okay, if for example, if I have m equal to 1, then when x is equal to d, so I get sine pi. Sine pi means 180 degrees. So one half cycle variation. If I have m equal to 2, then sine 2 pi. Okay, so this will become sine 2 pi. Even though sine 2 pi is also 0, but the thing is, so there is a 2 pi variation. So the distance between this is 2 pi. 2 pi means one full cycle, right? So I get two half cycles. Okay, the variation will be like this. So I'll draw like this. Okay, so when m is equal to 0, we will not get any variation of Ey. Okay, this is the variation of Ey. So there is no Ey variation. When m is equal to 1, right, I will get a variation of one half cycle. One half cycle. So 0 to pi. Okay, so this is 0 to pi. That means, right, my variation of Ey will be like this. One half cycle variation. Now, if m is equal to 2, right, m is an integer. So if I have m equal to 2, then I will get a variation of, right, 2 pi radians, isn't it? M equal to 2 pi. So that means 0 to 2 pi variation. So I will get two half cycles inside my waveguide. Okay, for the Ey. So if m is equal to 3, then I will get three half cycle variations like this. Okay, so right, this is for m equal to 2, this is m equal to 1, this is m equal to 0, and this is m is equal to 3. Okay, so here, right, based on the value, right, the field patterns will be like this, isn't it? The field patterns will be like this. Okay, so based on the value of m, right, the number of half cycle exertions of the Ey are going to change. Okay, so for the same pattern, for the same, everything is same, only based on the number of, right, the value of m, the number of half cycles, right, exertions in the waveguide are changing. So that is a very important factor for us. Okay, how the field is going to change inside the waveguide, isn't it? So it's a very important quantity. So therefore, we call this m, right? Whatever the integer we took, the constant we took, this m is called as the mode order or order of the mode. Okay. So right, each of this, right? So when m equal to 0, whatever the field variation I get, that is called as one mode. Right? When m is equal to 1, this will be another mode. Right? For each m value, whatever the tm wave, okay, sorry, whatever the t wave, right, we get the field pattern or the field, whatever the t wave generated for each m value is called as a different mode. Okay, so different mode of propagation. So when I have, right, so okay, when I have m equal to 0, I will get what a wave, the mode of propagation is said to be te0 mode. Okay, so when m is equal to 1, right, the mode that I am getting, that is the TE wave is going to propagate in a mode called as TE1. Okay, what is this TE1? TE1 means m equal to 1. So that is, there is a 1/2 cycle variation along the right length of the waveguide. Okay, so that's what I get. Similarly, for m equal to 2, TE2, m equal to 3, TE3. Okay, so this m value basically represents the order of the mode. Okay, mode order, or it is also represents the number of half cycle variations of the field inside the waveguide. Okay, so this is the variation. This is the field pattern for right EY. Okay, for different values of m. Similarly, if I look at the HZ, okay, so HZ, if I look at the HZ, right, so we can see that HZ is basically a cosine variation. Okay, so cosine variation. So therefore, at x is equal to 0, right? At x is equal to 0. This is x equal to 0, and this is x is equal to right d. So when my x value is 0, okay, so I will get the maximum value, right? So cosine will be maximum. Okay, right? Next, what happens? Next, what happens when x is equal to d? So cos of m pi, cos of m pi. M pi means m is an integer, so it can be pi cos. So if m equal to 1, it represents cos pi, which is minus 1. Okay, right? 2 pi, which is right. 2 pi means 1. Okay, then 3 pi, which is minus 1. So what we can say is, again there will be a maximum value of opposite polarity, isn't it? So therefore, right, the variation of right will be a cosine variation. Okay, the variation of right, the variation of Hz is basically a cosine variation inside the waveguide. So it is maximum here, right, and it is right opposite here. Okay, so it is representing a cosine variation. Okay, again this is just one cycle. Remember, right? If m is equal to 1, there will be one cycle like this. If the m value is equal to 2, so I will get two variations inside the waveguide like this. So the variation, the field pattern is right cosine here. Okay, for Hz, this is for Hz. Okay, so Hz varies as a cosine function. Okay, whereas Ey varies as a sinusoidal function. Next, similarly, if I look at the Hx, okay, so Hx, look at the Hx. So Hx also is a function of sine, so it is similar to that of Ey. Okay, so therefore the field pattern will be a sinusoidal field pattern, and it depends upon the m value. So if right, if m is equal to 1, I will get like this. Okay, if m is equal to 2, I will get like this. If m equal to 3, I'll get like this. Okay, so based on the m value, the number of half cycles inside the waveguide will change. Okay, so this is the field patterns, right? This figure is the field variation or the field pattern of Ey. This figure is the field pattern of Hz, and this figure is the field pattern of Hx. Okay, Ey follows a sinusoidal variation, sine wave variation, so it is like this. Okay, Hz follows a cosine variation, which is like this. Okay, and Hx follows a right sinusoidal variation, which is like this. Okay, so right, this is the field patterns of the TE waves for TE waves. Okay, so clear with this, right? This is the first characteristic we have, right? The field patterns, right? The visualization of the field in terms of right the x value. Okay, as a variation of x. Okay, so right, I think this is clear. Yeah. Now let us go to the next right. Next characteristic feature, which we already covered a little bit. So that is the mode order, and the minimum mode. Okay, and the minimum possible mode, right? Minimum possible mode. Yeah. So as I just told you, so what is mean by mode order here means it is the generally right right we can define as the mode order represents the number of half cycle exertions, number of half cycle exertions made by the wave, made by the field, made by a field inside a waveguide, inside a waveguide. So right, how many number of half cycles, okay, how many number of half cycles are exerted, or how many number of half cycle variations are appearing for a field inside the waveguide is called as the mode order. Okay, it's called as the mode or mode order. Okay, so generally we represent it with the m value, right? So okay, the m that comes in the field patterns is basically defined as the mode order. Okay, so this m value, right, this m value decides how many number of half cycle variations will be there for a particular field inside the waveguide. Okay, so that is basically, it decides the pattern of the field. Okay, okay, how does the field appear, how does the field varies inside the waveguide is decided by this m value. That is why, okay, for each m value we get a different mode configuration. Okay, we get a different mode configuration. So if m is equal to 0, right, we get a TE0 wave, right? If m is equal to 1, we get a TE1 wave, like this. So for each m value we get a T, right, a different wave characteristics, all right, altogether. Okay, so the characteristics of the wave also, right, are hugely influenced this by this mode order. Okay, so that is the importance of or significance of this mode order m value, right? In simple, we have to remember what is meant by mode. Means the mode is an integer value, right, which tells us how many half cycle variations are there for a particular field inside the waveguide. Okay, so this basically tells us what is the field pattern or the field structure inside the waveguide. Okay, so that is about the mode, right? Now, for every waveguide there will be one, right, lowest order mode that will be separated, that will be supported by this waveguide, and beyond this lowest order all the other right higher modes will be supported. So for in case of TE wave, what is that minimum order? Let us verify. So the minimum possible, because m is an integer, the minimum possible value of m is 0. Okay, so right, m is equal to 0. But when I substitute m equal to 0 in EY, HX and HZ, all of them becomes 0. Okay, so EY becomes 0, HX becomes 0, HZ also becomes 0. Okay, most importantly, EY term, right, even though HZ does not become 0, right, EY will go to 0. Okay, HX will go to 0. Okay, these two values go to 0 because EY is a sinusoidal variation. So sine of m pi by d, right, this is what we got. Okay, similarly this is also a function of sine m pi by d. So whenever m is equal to 0, so sine 0 is always 0. Okay, so therefore EY and HX will become 0. So since EY is becoming 0, right, already EX is 0, we don't have an EX term and we don't have EZ term. So EX is equal to 0, EZ is equal to 0 for a TE wave, isn't it? So for a TE wave, already we derived EX is equal to 0, EZ is equal to 0. Now we are getting EY also becoming 0. This means the electric field components inside the inside the waveguides are completely 0. So all the field components are 0. That means the electric field does not exist. So if the electric field does not exist, then there will be no question of electromagnetic wave inside the waveguide. Okay. So right, therefore m is equal to 0 cannot exist in case of TE waves. Okay. So we will not get any wave propagation when the order of the wave is 0. Okay. So that is TE0 wave cannot propagate through the waveguide. This is the most important conclusion, right? So TE0 wave cannot propagate through the waveguide. It is possible to get m equal to 0, but we will not have any field components. So the wave cannot propagate through the waveguide if m is equal to 0. Okay, so that is a more important point, right? Next point is, now let us check with m equal to 1. So when I put m equal to 1 in the equations that we have, so we get, right, right, all the components, that is EY, HZ and HX, all of them will be non-zeros. So there will be some values. Okay, so sine pi by d, we will get this term as sine pi by d into x, and this is also sine pi by d into x, right, and this is cos pi by d into x. So all of them are non-zero values. Okay, So there will be some variation, right? Depending upon the x value, there will be a sinusoidal variation of all these components, right, along the x-axis. Okay, so all of them will exist. That is what we mean. Okay, so there is a wave, right? There is a variation of these components, and the wave exists. Okay, so therefore, right, the m equal to 1, that is the TE1 wave, okay, can propagate through the waveguide. Okay, so can propagate through the waveguide. Okay, so therefore the minimum mode that is supported by the TE wave or for the TE configuration is TE1. Okay, so in case of a planar waveguide, the minimum mode that is supported by the waveguide is TE1. Okay, so we should have the minimum value of m should be equal to 1. Okay, so m equal to 0 is not supported for the TE transverse electric case in case of the planar waveguide. Okay, so these are the two characteristics, right? So we defined what is mode order. Mode order represents the number of half cycle exertions by the field inside the waveguide, and then we have discussed the minimum possible mode. Lowest possible mode that is possible is m is equal to 1 or TE1. Okay, so this is the thing, right? Now let us go to the next characteristics, right? The most important characteristic is the cutoff frequency for the right waveguide. Okay, so cutoff frequency for the waveguide. Okay, so one point that we have to understand, right, or I would like to bring to your notice here is, so there is one very important difference between the transmission line and the waveguide. Yes, waveguide is also an example of transmission line, but the general transmission lines that we take, that is the two-wire transmission lines like twisted pates or coaxial cables. Okay, these two-wire transmission lines. Okay, so that is, you have a transmission line of two wires, isn't it? Okay, so this is a two-wire transmission line. So these two-wire transmission lines supports all frequencies to be transmitted through it. Okay, and then they will transmit or they will propagate all the frequencies, right, okay, through them. So you can transmit any frequency. There is no problem at all with a right two-wire transmission line, which is basically a coaxial cable or an optical fiber cable, or you can take it as a right twisted pace. Okay, twisted pace or two-wire pace. Okay, so that is the thing, right? But whereas waveguide, if I consider a waveguide, even though here we can say that the parallel plane waveguide, okay, the parallel plane waveguide is actually having two plates, right? So you can say that it is similar to that of a transmission line, but right, but that is not the case, right? That's why we said parallel plane waveguide is generally right a theoretical assumption. So more practical waveguides such as rectangular or circular, right? So we don't have right a two-wire structure. So what rectangular waveguide, if I consider a rectangular waveguide like this, right? So okay, this it's a closed box, isn't it? Rectangular waveguide is a closed box. All the four sides are closed, okay, and they are connected to one another. So right, a rectangular or a circular or a elliptical waveguide is basically a single wire structure or a single conductor structure. Okay, so for example, if I consider a rectangular waveguide like this, so all the four walls are interconnected to each other, so all of them are just one conductor. There is no second conductor here. Okay, so that is the difference, primary difference between a waveguide and a normal transmission line, a two-wire transmission line. Okay, so a general transmission line has two pairs of conductors, so one above, one below, okay, and separated by a dielectric medium. Okay, so because of this structure, it will support all frequencies to be transmitted through it. Whereas waveguide, right, practical waveguides, they are just one right wire structures or one conductor structures, because the entire body of the waveguide is interconnected. There is no separation between, right, there are no separation between the two plates. There are no two plates now. There are four plates. 1, 2, 3, 4, right? And all of them is a single structure. Okay, right? There is a hollow space between them, and that is airfield. Okay, Okay, so all the four walls are interconnected, right? So it is single conductor itself. There are no two conductors there. Okay, so therefore waveguide, right, is little different from when compared to the transmission line. Okay, and the primary difference that comes here is that waveguide will support only certain frequencies to be transmitted through it. Okay, so what are those frequencies, right? And right, what is this concept we will discuss, right? So let us go to the topic. Yeah, so right, the point that we have to understand is waveguide is an open conductor structure, and because of this, right, not all frequencies can travel can propagate through it. Okay, right? So yesterday, when we right in the previous lecture, when we derived the expressions, when we are deriving the expressions for the field patterns, we assumed a constant. That constant is represented as h square. So h square is equal to gamma square plus omega square mu epsilon. I think if you remember. So this is right. We assumed the value of gamma square plus omega square mu epsilon as some constant, which is h square. Okay, so let us take that expression again. So from this, gamma square is equal to h square minus omega square mu epsilon. Okay, or gamma is equal to root of h square minus omega square mu epsilon. Okay, so this is the thing, right? So from this, now assuming that this constant h is same as that of a, the constant a that we took for right the calculation, which is equal to, which we got as m pi by d, isn't it? So we got the value. Okay, so let the value of h, we can also derive that. That's not a big issue, but it's not required. So we get the value of h as m pi by d. So let us substitute that here. Okay, so gamma is equal to root of m pi by d whole square minus omega square mu epsilon. Okay, correct. So this is the expression we got, right? Now in general, right, the gamma, what is gamma? Gamma means, right, propagation constant. So it is right a sum of alternation constant and phase constant beta. So we can express gamma as alpha plus j beta. So alpha plus j beta is equal to root of m pi by d whole square minus omega square mu epsilon. Okay, clear with this? Yeah. Now from this, let us take this equation again. So alpha plus j beta or gamma. So gamma is equal to alpha plus j beta is equal to root of, okay, m pi by d whole square minus omega square mu epsilon. Okay, right. Now see here carefully. So this is the expression that we got. We took the simple equation of h square is equal to gamma square plus omega square mu epsilon. From that I have written the value of gamma, and I have assumed h is equal to m pi by d. We can derive it. Okay, it's a simple derivation. Okay, but not required. So we will get h is equal to m pi by d. Okay, so I have substituted that and I got expression like this. Okay, even if you put h square here, it doesn't matter. Okay, it doesn't matter. Right now, right, listen carefully. So if I get two possible cases here. Okay, so first case is, case one is if omega value is very less. Okay, if omega value is low. Okay, let us say that if the omega, what is omega? Omega is nothing but 2 pi f. So let us say that the signal frequency is low. Okay, so if it is low in such a way that the value of m pi by d whole square is less than, right, sorry, m pi by d whole square is greater than omega square by mu epsilon. Okay, so because this is a low value, we are assuming that m pi by d whole square is more than omega square mu epsilon. Okay, so this is more when compared to this. So what will happen? The root inside, right? This is more when compared to this. So therefore, this will become a positive value, and therefore gamma will be purely real and positive. Purely real and positive, isn't it? Okay, so gamma will become, right, purely real and positive. Okay, so if my omega, that is the if angular frequency omega is low, right, is a small value, is low, let's say it is a small value, right, such that what is the case, such that, right, okay, so if such that if m such that the m pi by d whole square is more when compared to omega square mu epsilon, okay, is more than omega square mu epsilon. If that is the case, then the gamma value will be purely real and positive. Okay, so this implies that because this is purely real and positive, this implies that alpha plus j beta, it's a purely real, so beta is equal to 0. So alpha will be a positive value, alpha will be a positive value, whereas beta will be equal to 0. Okay, so alpha will be purely real, that is alpha will be a positive value and beta is equal to 0. So therefore in this case, right, what is happening, there is attenuation and there is no phase shift. Okay, so phase shift is not there, so phase shift is not there, right, only attenuation is there. So therefore the signal will get attenuated. Okay, after some time the signal will become 0. Okay, the signal undergoes continuous attenuation, right, and it will become 0. Okay, so this is alpha, right, so as, right, x value increases, alpha increases, so signal will after some time, right, after some time the signal, right, so signal amplitude will continuously decrease and it will become 0. Okay, so as the wave propagates through the waveguide, after some time the wave will become 0, the wave will become 0 and it's get continuously attenuated. Okay, so that is what is going to happen whenever the frequency is low, right, when the frequency is low, then m pi by d whole square will be more when compared to this. Okay, so whenever this happens, the signal, right, the signal or the wave will not propagate through the waveguide. That is the conclusion from this. Okay, right, now let us have the case 2. What is case 2? Case 2 is when if omega is very high. Okay, let's say the value of frequency that you are taking is very high. Okay, so if the omega value is very high, such that what is the case, m pi by d whole square is less than omega square mu epsilon. Okay, so if m pi by d whole square is less than omega square mu epsilon, okay, in this case what is happening, the gamma that I take, right, the gamma that I get, okay, so because this is more when compared to this, so I'll get a negative value, right, so root of negative value means it's an imaginary term. So in this case gamma will be purely imaginary, so here I will get the gamma value as purely imaginary. Okay, so when I have purely imaginary term, so gamma value will become purely imaginary. So in that case, right, gamma becomes purely imaginary. So in this case, right, okay, what happens? So alpha will be 0, whereas beta will be a positive value. Okay, beta will be some positive value, some value will exist. So therefore, what we can say in this case, the alpha is 0 means the wave attenuation, the attenuation offered by the waveguide is 0. So the wave will propagate through the waveguide without any attenuation, only with some phase shift or delay. Okay, so here the wave propagation happens. Okay, so the wave propagation happens. So therefore we can say that the waveguide that is there, it is acting as a high pass filter. Okay, it is acting as a high pass filter. So up to certain frequencies, right, where, okay, up to certain frequencies the wave will not get propagated through the waveguide. Okay, after certain frequencies the wave gets propagated through the waveguide. So right, up to certain frequencies, right, the wave gets attenuated, right, because the omega value is less, right. After certain frequencies the omega value will become more, right, and the gamma becomes imaginary, and here the wave propagation starts. Okay, so this frequency where the transition happens, okay, where the waveguide starts, right, passing the signal. Okay, so or you can define it in another way, it is the minimum frequency, right. So the minimum frequency that gets propagated through the waveguide, okay, that gets propagated through the waveguide is called as the cutoff frequency of the waveguide. Okay, so right, every waveguide based on the dimensions, right, there will be a minimum frequency beyond which the propagation starts. Okay, so that minimum frequency or that frequency which gets propagated through the waveguide is called as the F minimum frequency or the F cutoff frequency. Okay, so that will come, okay, right, whenever the m pi by d whole square is equal to omega square mu epsilon. Okay, so whenever these two terms become equal, then my right gamma will be 0. So that means alpha will be 0 and beta also 0. So my propagation starts. Okay, my propagation starts. So that is the point where which we call it as the right cutoff point or the minimum frequency point. Okay, right? Yeah. So from this equation, I can write omega square is equal to 1 by mu epsilon into m pi by d whole square, or omega is equal to 1 by root mu epsilon into m pi by d. Okay, right? M pi by d. Okay. Next, or because we can write omega as 2 pi f. So 2 pi f is equal to 1 by root mu epsilon into m pi by d. So f is equal to, right, 1 by 2 pi, 1 by 2 pi, 1 by 2 pi into root mu epsilon into m pi by d. So pi gets cancelled. So I get f is equal to the derivation. I get f is equal to m by, right, 2d root of mu epsilon. Okay, so this is the cutoff frequency or the minimum frequency, F minimum or F cutoff. So F minimum of or F cutoff is given by m by 2d into root mu epsilon. So right, this is a very important. So this is the frequency, right? This is the frequency beyond which, right, the signal gets propagated through the waveguide. Okay, beyond this, right, the frequency